Hello, I would like to welcome everybody. Let me present our research coefficients of the Williams-Bower expansion of the near-corrective stress field of continuum fracture mechanics at the nanoscale. We would like to present our analysis of the stress field in the neighborhood of the corrective by molecular dynamics simulations implemented in a classical molecular dynamics code length, large-scale atomic molecular massively parallel simulator. The molecular dynamics simulations are aimed at computing continuum linear elastic fracture mechanics parameters such as stress intensity factors, T-stresses, and higher order coefficients of the Williams series expansion of the stress field in an isotropic linear elastic material. The main objective of our study is the comparison of continuum and atomistic approaches for the estimation of the near-corrective fields. Stress intensity factors, T-stresses, and higher order coefficients of the Williams series expansion for a copper plate with a central crack under mode 1 and mixed mode loadings are evaluated by atomistic modeling. We perform the wide class of the computational experiments in labs. The atomistic values of stress intensity factors and higher order terms of the Williams series expansion are compared with the values obtained from the classical solutions of continuum linear elastic fracture mechanics. And it is shown that the continuum fracture theory can successfully describe fracture and the near-corrective fields even at extremely confined singular stress field of only several nanometers. The circumferential distributions of the stress tensor components from atomistic modeling are retrieved and compared with the angular distributions of the stresses from linear elastic fracture mechanics. The comparison shows good agreement between two approaches. Thus, we would like to determine stress intensity factors and higher order terms of the Williams series expansion by atomistic simulations. First, I would like to show the classical Williams-Bower expansion. Here, A and K are amplitude coefficients related to the geometry of the cracked specimen, load and mode. Angular distributions of the stress tensor components are described by well-known functions, and the displacement fields around the crack tip can be presented in the asymptotic form and we would like to evaluate the coefficients of the Williams series expansion by molecular dynamics simulations. Here I would like to show the geometry considered, and we consider the plate with the central crack under mode 1 and mixed mode loading. The details of molecular dynamic simulations are given here, and the results of our modeling are presented here. You can see the stress tensor components for mode 1 you can see the stress tensor components for the cracked plate under mixed load at 5, 10, 15, 20, 25 and 40 picoseconds. Having obtained the stress tensor components, we can estimate the fracture mechanics parameters, the parameters of the conventional continuum fracture mechanics. In order to do it, we consider different ring areas surrounding the crack tip, and we use the stress tensor components to calculate the coefficients of the Williams series expansion by the over-deterministic method. And the results of our comparison are given here. The blue dotted lines show the solution of the linear fracture mechanics, of conventional linear fracture mechanics, whereas red dots show the solution obtained by molecular dynamics approach. You can see that the stress tensor components show good agreement, and you can see here the distributions of the stress tensor components for mixed mode loading. Again, red points show molecular dynamics simulations, whereas blue dotted line show the results of continuum linear fracture mechanics. You can see here the descriptions of these figures. Here you can see the values of the mixity parameters considered. And here I would like to show again different ring areas used for the estimation of the fracture mechanics parameters. And finally, I would like to show the normalized coefficients of the Williams series expansion for the stress field in the vicinity of the crack tip found by molecular dynamics method and by the analytical solution for the infinite plate with the central crack. You can see that the results show good agreement, and results are very close to each other. Finally, I would like to summarize our results. First, we evaluate the higher order coefficients of the Williams series expansion of the classical fracture mechanics, and we keep in the Williams series expansion 15 terms, and these 15 coefficients have been determined by molecular dynamic simulations. And we can say that a good agreement between stresses on both levels of descriptions is found, and the applicability of the conventional linear fracture mechanics in nanometers range is demonstrated. Thank you very much for your attention.